go ahead and get started.
Thank you, Stacy. Good evening, everyone. This is Mark Storlie. I serve as a swine field specialist for Northeast Iowa. I'm your host. I would welcome you to our webinar, Prepping Your Barn for Winter, Putting Checklists into Practice. And so tonight we're going to visit with Brett Ramirez. Dr. Ramirez is an associate professor in the Department of Agricultural and Biosystems Engineering at Iowa State University and is the assistant director of the Egg Industry Center. He leads an integrated research and extension program that generates and shares science-based information following engineering principles to guide the design and management of our controlled environments for food-producing animals. His scholarship focuses on facilities and environmental management, precision livestock farming, and management for catastrophic events. Dr. Ramirez's extension program consists of applied research and programming to provide evidence-based information to enable informed decision-making that supports sustainable and efficient animal production systems. Brett, we look forward to your words of wisdom as you review elements of checklists that producers can put into practice to improve the efficiency of their swine facilities.
Thanks, Mark, and thank you all for taking the time out of your busy schedules at this very busy time of year to tune in and learn about more details on how to get your swine facility prepared for the cold, dreary upcoming winter months. But I guess not cold and dreary yet, but I know we will be here soon, unfortunately. So for today, I'm going to kind of run down, kind of put the checklist into practice, kind of go through some best practices and maybe a lot more of the why we have those things on the checklist and why we do it that way. So I'm going to kind of dive on in and learn more about how to do this. So first, I'd just like to start with having access to the checklist if you haven't already seen it. I provided a QR code there. You can give that a scan and it'll take you right here to the winter checklist. Or another easy way to get to it is go Google the ISU extension store and then type into the search bar the fact sheet number and it will pop right up. But just an overview of the checklist, it's a front and back two-sided checklist, and it's going to cover a range of topics that will apply to a lot of barns, but not all barns. But it's something that's really useful that can help guide you through this process, as it's easy to get hung up with a lot of things at this time of year. And this is really going to kind of provide that kind of step-by-step what to check, how to check it, which we'll cover today, and then being able to use this repeatedly so you can always be prepared each winter.
Brett, if I could briefly interject, please, certainly, if you have questions, put them into the chat box. That way, we certainly want to address any thoughts or questions you have as we're going through the presentation. Brett might be able to address it firsthand, or otherwise at the end of the session, we want to make sure to cover your interests.
Yeah, great point, Mark. Welcome questions. Just with my current monitor setup, Mark, if you can flag me some way to stop, I'd be happy to stop and address that question. It just might be a little hard for me to catch them as they come in.
Will do.
Okay, so to kick things off, getting barns ready for winter and just general operational, it can be easy. There's a lot of, I'd say, some obvious things, but it really comes down to troubleshooting and knowing when something isn't right. So this might be a little bit after a checklist has already been used, but the thing is, if you look at some of these pictures, it should be, hopefully after this might help build that intuition, but we really want to be able to recognize when something's not right. We want to get on it early, and we don't want that problem to build, because a lot of things, it might seem trivial at first, but as time keeps going on, as the barn keeps aging, those issues tend to compound. So it's also important during this checklist operation and as you're troubleshooting is to make sure you have the right tools, and I'll go over that a little bit. Again, maintenance helps a lot of things throughout this checklist. If those things are already being done routinely, that really cuts down on how many things have to be done to prepare for winter. And again, key thing, have a checklist. It really does help guide, because ventilation usually isn't one of the things that most people are intuitive about or have a lot of training on. And so having that checklist really helps direct where that effort needs to be spent when it comes to preparing a barn for winter or just doing general troubleshooting or ventilation operation management. So the key point here is that really a lot of our success during the cold weather and at minimum ventilation can be achieved by reducing leakage, and I'll touch on that more. I also like to remind everybody to, before they get into the barn, take a look at the pigs. They're going to be your best indicator if they're too cold, too hot, or just right. They're also going to kind of give you that indication of behavior. What are they doing? Are they agitated? Are they all lying? Are they all, doing some activity? That's going to, again, kind of give you that information if the environment's not quite right. We also need to check sensors. If we do make changes, make sure they're small and make sure that we have a frame of reference or some data that we can compare to what we did before the change and after the change. And I also always like to point out, the controller doesn't have all the answers. That's typically the first spot we stop at when we're trying to do troubleshooting, but it's often maybe the problem, but it might compound an error, but oftentimes it's something in the barn or with the facility that needs to be checked in addition. So key take home message, and I just talked about this, but kind of laying it out a little bit more. Look at the pigs and note their behavior. Ask yourself, what's their lying pattern? Are they avoiding certain areas? Are they evenly distributed, doing different activities? Are they moving around? Again, this is going to give you the best indication if that environment's right. Too hot, too cold, maybe the gas concentrations are too high, maybe there's a cold draft on them, but the pigs are going to be that best feedback. And again, another important part if in this troubleshooting part is we always have to keep in mind that what the outdoor temperature is and what our set point is. Then we can go to the controller, note the stage, what equipment's being called for, fan speeds, what's on, what's off, what's supposed to be open. And then that's when we ask ourselves, does this match with what's going on in the barn? And so we kind of have to build that intuition for based on outdoor temperature and set point, what should be going on, and does that seem reasonable? And then the last one is, again, I'm going to harp on this a lot, but routinely inspect equipment and perform routine maintenance to really just make sure everything is working. I've been in a lot of barns recently where I go in and stuff just doesn't work. Numerous reasons why, but again, especially going into winter, we need to make sure things that are supposed to be on or variable are actually performing that way, or if they're supposed to be off, make sure they're switched off at the wall and make sure things are being done the way they're supposed to be. So quick background on ventilation, just because it sets the stage for what we're going to talk about. Really, the basics of ventilation is it affects everything in the room. Simply put, we bring fresh air in, we want to mix it thoroughly, and then we want to exhaust it. So ventilation can affect humidity, air temperature, drafts, condensation, airspeed across the animals, odor and gas concentrations, pathogen levels, amount of combustion fumes. But as long as we bring that fresh air in, we mix it to collect all that stuff, and then we take it out. That is the basics of the ventilation process. And when we fail to provide any of those three steps, we're going to lead to inadequate ventilation. So what controls and determines ventilation rate? This is just a general overview, is that as outdoor temperature increases, so does our ventilation rate. And that makes sense on how we stage and set up our controllers. But what we're focused on is that as these temperatures get colder, we're going to be more on the colder side of the balance temperature, where our primary focus is going to be ventilating for moisture control, which is our minimum ventilation rate. And at this time, our goal is really to remove the excess moisture being generated by the pigs and any of the noxious gases created by pigs' manure and then combustion from unvented heaters, and make sure that's being exhausted from the barn. The result of underventilating leads to an accumulation of these, and then that can cause our potential health problems, potential performance. Again, when we get into the colder weather, we tend to think a little bit more about ventilation rates. I always like to remind everyone that ventilation rates, such as like 1.5 or 2 CFM per pig, are good design guides. And so that's where I start if I'm trying to pick the number of fans I need to operate, or the speed that they need to operate, or how many fans I'm going to have on. I'm going to try and start with the CFM per head, but really when we get into the operation, especially during winter, is we want to focus on the pigs and using measurements of temperature, humidity inside the barn, and then adjust our ventilation system based on that feedback. And that's what's going to lead to good environmental management inside the barn. I don't get too hung up on making sure that I'm achieving exactly 2 CFM per head in middle of winter if I've got, pigs just placed. I'm more focused on making sure we've got a nice, warm, dry environment inside that barn. Again, as we move into winter, we're always faced with this conundrum of energy efficiency versus air quality. They can both be friends and foes. We want both, right? We want to save money through using less propane, but we also want a good environment with, low ammonia, low CO2, low CO, low humidity that all affect that air quality aspect. So we need both. And so the problem is as we increase ventilation in the cold weather, that's going to increase our energy demand for electricity for the fans and also the propane to heat that barn. As we decrease ventilation to kind of save on that energy, it's going to cause the concentration or our air quality to get worse, concentrations to increase and our air quality to get worse. So really we're trying to find that black dot, that optimum ventilation that kind of limits our pollutant concentrations, also at some level of energy usage, and provides that acceptable air quality. So that's kind of what our goal is. Again, troubleshooting in the barn. We have a lot of different tools in the toolbox. Some of the most frequently used ones are going to be this portable weather meter. This is just an example of one. This will measure temperature, humidity, and airspeed. Temperature is good for checking sensors or what the controller is saying. Humidity is good to check if we're under or over ventilating. And then airspeed is very useful for measuring the airspeed coming out of our inlets to make sure we're getting a good jet for mixing and we're not dropping cold air on the pigs. The smoke sticks are also great for visualizing that drop or for identifying any leaks or drafts. The smoke's going to move as that air with the air, so it's very helpful for visualizing airflow. Tape measure for measuring inlets, a manometer or static pressure gauge if that's possible. Laser tachometer is good for checking fan speeds. If you happen to know what the variable speed percentage is and what the corresponding RPMs are, the laser tachometer is a good way to verify that. Infrared temperatures gun is good for checking warm and cold spots, so underneath brooders, or if you have a thermal imaging camera, you can also look for cold spots, which is going to indicate like drafts on some sidewalls or end walls. Volt or multimeter is good for, again, checking current or power or at the controller. And then gas detection tubes or sensors or some newer technology that's a little bit more useful for if we want to monitor ammonia or carbon dioxide inside the barn. So I'm going to first dive into fans. Again, probably the most important part about going into winter is making sure our pit fans are maintained, clean, and functioning properly. Since we're in cold weather, we're going to be at a lot lower ventilation rates, which means we're going to be running our pit fans almost all the time. And so that's why, since these fans are going to be running 24/7 throughout winter, they need to be in tip-top shape and working the best. The other problem is that if we push this off too long, they're going to be covered in snow, and nobody wants to walk around their barn with a 6-foot snowdrift and try to see if their pit fan's on or if it's even clean. So it's best to get on pit fans early while the weather's still nice and we still have an opportunity to clean them. So again, also given this time of year, if we haven't had the chance to pump out yet, I know there's been some rain moving through the area and all sorts of different weather things going on across the state. We always got to make sure in a pump out that we leave at least 2 feet to allow effective opening to move air into the pit fan. So as that manure starts to come up, or if there's foaming, that's going to cinch that spot down, and that's going to cause a high static pressure or a high resistance that's going to have to make that fan work harder. So you can see in that picture that fan's actually running at 100%, but you wouldn't know it just because of those shutters not open, and I'm sure those blades are barely spinning because there's such a resistance that fan's having to work against because that manure is so high and there's no real effective opening to get air through that fan. So other things we want to do, getting back to the checklist, we want to turn off any unused fans, make sure they're off at the wall, and then they can be off at the controller. A nice thing I see a lot of people do is put some plastic up behind the shutters. I know it's an extra step and people tend to lose the plastic. It gets dirty, torn, but by putting plastic up behind those shutters, you can really decrease the leakage through those shutters in winter, and it helps create a pretty nice seal. It doesn't really add much in terms of insulation, but it is a nice barrier to stop cold air from leaking in, especially on that last pen. We want to just make sure fan blades are clean, blades aren't rubbing, motor housings are clean, wire guards, just again, clean fans operate better and provide the performance that we expect. Keeping shutters clean, it's always important. We want to just make sure everything's in good shape, and discharge cones are also installed and not broken, and also clean and properly positioned on the fan. All right, moving on into inlets. So usually getting ventilation rate is easy. It's easy to make sure our fans are running, and everything's on, and we're getting close to the desired rate. What gets really tricky is how to make sure we get that cold air distributed correctly. So when we bring cold air into the house through the attic, or through the soffit, then through the attic, and then through the inlet, we need to make sure that cold air comes in, it has a chance to warm up, and then by the time it gets down to pig level, it kind of slowly diffuses through the space, and it's not really creating any drafts on the pigs. We also want this air to be distributed uniformly. We don't want hot spots or cold spots throughout the house. And so by getting a good air jet and uniform mixing, we can really make sure we got a nice even temperature throughout. We do not want it to cause excessive drops in the house temperature. We don't want it to cause drafts, and that's going to be our goal for the next couple months. And so we have to make sure that we're achieving the right static pressure, which means we're getting the right airspeed, and that's creating that jet that has a chance to warm up as it moves through the house and then slowly diffuse through the pig space. So our goal, especially during minimum ventilation, is around 600 to 800 feet per minute, and that's going to make sure that we get a good jet for mixing. So what does this look like? The upper left picture shows sufficient static pressure across an inlet. So you can see as that jet comes in, it stays above the pigs at a higher speed. And then as it reaches kind of the sidewall of the barn, it's going to slowly start to come down. And then as it gets down to the pigs, it's going to pick up all that heat, moisture, and gases. And then the fan's going to exhaust it from the barn. So what happens when we don't have enough airspeed? So maybe like 200 to 300 feet per minute at the inlet, we're going to see that picture in the bottom right. That cold air is going to come down and drop because it doesn't have enough momentum to shoot across the ceiling and warm up. It's going to fall down, and then it's going to create, a cold, wet, drafty spot where the pigs are going to avoid or turn it into their dunging area because they know that's the worst spot in the barn. So what also happens in this is that on the other side of where that cold air is dropping, no fresh air is going to mix in there, and so it becomes a warm, kind of stale spot on the other side of the pen, which doesn't really get that exchange and never really mixes well, and it's just going to create an ununiform barn that it's going to just create issues for the pigs. And also with that, poor mixing can also potentially increase your energy costs because heaters might operate more frequently depending on where they're at. If the sensor's placed in the wrong spot, it's going to cool down faster or stay warm, and it's just going to lead to an overall worse environment for the pigs. So again, when we don't have enough airspeed at the inlet, it's going to come in and fall down to the ground or to the slats, and it's not really going to mix and have that chance to warm up. So that usually happens about 4 to 6 feet. So if it's over the center alley, you'll see that first about 2 feet on each side of the alley is going to be usually wet. It's going to be the dunging area, and it's going to be the least desirable spot of the pen. So we always want to make sure we get that 600 to 800 feet per minute so we avoid this situation. And so what can we do to help prevent this? So the key here, and I'll get on more on this, but we have to reduce infiltration. So all the leaks in the barn are robbing air from going through our ceiling inlet. So we need to make sure the barn is sealed up tight to make sure we can direct as much air as possible through the ceiling inlet. Another thing that I see a lot of people do is they will close one side of their inlets on both roads. And again, what they're doing is reducing that opening and really driving more air through the other openings to really create that better air jet for mixing. So if we have a constant ventilation rate, the more we open that inlet, the lower the airspeed is going to be, and vice versa. And so that's how we can control and help set those inlets. We also, as we're going through this checklist, we want to make sure we take a look at the inlet housing itself and make sure we repair them. So if the inlet's hanging off the wall or it didn't get, or there's a screw missing, we want to make sure we get those tightened up. And if we can, add some caulk around the housing to, again, what we're doing is preventing leakage, and we're preventing air that's intended to go into that mixing pattern. Driving air into that mixing pattern and preventing leakage that's going to rob that air. Again, infiltration's key. Reducing infiltration is key. We need to take control of how the air enters the house and where it enters the house. And so we do that by making sure we tighten everything up. So like, for example, you look at the upper right picture of those shutters. Shutters notoriously leak. They can leak quite a bit, a lot more than one might expect, even though they're meant for backdraft protection. But again, putting plastic behind them is a great way to seal them up. We really want to, do our best to reduce all other unplanned openings from allowing air to enter into that barn. Things of looking around where the curtains seal, around doors. That middle door picture is a funny one. I saw I think last year that somebody just spray foamed their door shut. That might be a little bit overkill for some people about tightening their barn up, but that would be one way to do it. Otherwise, we can see doors like that in the thermal image where, all those cracks around the door, they're going to show colder, and, it's just letting air into the barn that's not going through where we want it to go in the ceiling, through the ceiling inlets. All right, a little bit on controller settings. So I know most people all have different controllers, and it's really hard to hit specifics for each controller. I'm by no means an expert on each controller, but what I'll talk about is kind of some general settings that are applicable to all controllers. You'll just have to make sure you use the right terminology that's associated with these settings in your particular controller. And I'm going to mainly talk about controlling of forced air furnaces, or most likely your LB White, because these settings are critical to reducing energy usage in the barn during winter. And so we'll mainly focus on the offset temperature, so the temperature before the heating starts. And so basically we can think of the set point as the separation line between heating and cooling. And so depending on the controller, some have a heater on and a heater off temperature, or a heater offset temperature. And if there's a heater on and off temperature, there's also some sort of a differential associated with that. So below the set point is going to be our heating phase. And then the differential is the temperature difference between the on and the off temperature. In this case, 1 degree Fahrenheit. The heater offset is the temperature difference between the off temperature and the set point. So after the heater turns off, the room will continue to warm slightly. This occurs most in smaller rooms with large heaters, but it is also due to the time it takes for the heat to distribute, and then also for the time it takes the temperature sensor to respond to all that heat just added to the room. Typically, we're going to use somewhere between a 1 and 1.5 degree offset. And so that offset's critical because that allows that time for that heat to mix throughout the barn. So what we don't want to happen is that room temperature to keep increasing after our heater turns off. So we don't want to go past the set point. So if the offset is too small, in this case, if it's only maybe a 0.5 degree Fahrenheit, the temperature is going to overshoot the set point. And then what's going to happen is that minimum speed, or the minimum stage, or stage 1 fan, however it's configured, is going to increase, and then it's going to basically pull all of that heat that you just paid for out of the barn, and then it's going to get into a cycle of heat, cool, which is what we don't want to do. We want that heater to turn on, turn off, and we don't want to see a response from that minimum ventilation fan. So we call that like overrunning the set point, or there's a lot of different phrases for it. But if we see something like this happen, all we need to do is increase that offset, or make the heater off temperature and on temperature a little bit cooler to avoid this situation, because it can really waste a lot of energy. Again, a little bit on variable speed fans. A lot of times people ask, what minimum speed do I use? Does the percent reading on my controller mean percent capacity on my fan? Why does my system behave differently after I replace the fan motor? What are the consequences of using improper minimum ventilation settings? These are all excellent questions that are common throughout the industry. And so what we're going to do is try to clarify some of these and make some sense out of it. So trivia question for the evening: what does 50% speed mean on a controller? Is it 50% of CFM, RPM, voltage, or just a funny number? I'll say in most cases is most likely just a funny number, and it has no real indication to any of those three. And so that's where it's going to become more important to look at what does that mean for a particular controller, and what is the motor curve associated with that, and what does the fan performance look like. So typically what I recommend is that 50% speed does not equal 50% CFM. It tends to be a little bit less. 50% voltage to the fan does not equal 50% of the CFM or RPM of that fan. Every single motor that's out there is all going to react to the supplied voltage differently, and the minimum speed should never be under 50% of the RPM. If you get too low on the minimum speed from an RPM basis, that fan's going to have a struggle against higher static pressures or any headwinds, and it's not going to perform the way we want. In addition, this is all for standard triac controlled fans. Some of the newer fan, like the EC motors, are going to, it's different how they control their speed. But most controllers traditionally will control it by changing the voltage supplied to the fan. So how does the controller work with your variable speed fan? So you will punch in a motor curve number and a percent on the controller. It's going to translate that to volts, which goes to the motor, which translates that to energy to spin the fan. So make it run at a certain speed, and then that fan will deliver a airflow or CFMs based on that. And so the key here is that motor curve and making sure that this whole process goes smoothly and that it all matches up with what we want to do. So many people make the mistake of thinking that the percentage readout on the controller is the percentage of airflow that fan's going to deliver. This is not the case. The controller is going to produce a voltage which changes the percentage readout on the controller. The motor uses that voltage to operate at a corresponding RPM speed. Then that's what's going to correspond to the flow rate. So it's important, but it is complicated, and hopefully this is going to add some clarity. So as you go out and practice, it makes more sense. So this is a fan test graph for a fan set at different voltages. The 230 volts, that red line, is the full speed characteristics and flow versus static pressure for that fan. So most of the time in wintertime, we're going to operate somewhere between a 0.5 and a 0.05 and a 0.1 static pressure, just due to the inlets, soffit, pump out, and that. So we're going to have a slightly higher pressure than we might see in summertime. So as the voltage decreases, the RPM of the fan motor decreases, the ability of the fan to move air drops dramatically. So, so if you notice, as we decrease that voltage, that fan at those very low voltages are not going to turn against, say, a headwind or any other. Also notice that at half power, which would be right around 120 volts, that at a 0.1 static pressure, that it's closer to a third of the full output voltage. So again, it's not a 50% voltage equals 50% airflow. So again, motor curves are going to describe this relationship between the voltage supplied to the motor and the resulting RPM. There varies with every motor make and size, and different motor curves exist for all different motors. Even from the same manufacturer, might use different motor curves for different size fans, which have different size motors on them. So we really need to make sure we get the right curve to get the right ventilation rate, to make sure we don't overventilate, say, when we're at our minimum rate, and as that temperature inside the barn increases, that fan's going to ramp up smoothly. And so what that looks like, what we really want is kind of a nice straight line between the number on the controller and what our percent full output airflow is from that fan. And so we want it to just smoothly go up, but in reality, what happens is it's more like that red line. And so what that motor curve does is takes that red line and translates it as close to a linear relationship as possible. So for an APP 24-inch fan as an example, this just is a way to look at how your supply voltage versus motor speed versus fan airflow changes as that voltage supplied changes. So as you go from 230 volts to 190 4 volts supplied to that motor. That's a 46 volt drop. RPM changed by 100 and airflow changes by about 638 CFM. However, when you decrease voltage of that fan by only 33 volts, RPMs now doubled how much they change, and then airflow went up almost four times difference. And so that kind of shows that nonlinear relationship where that motor curve is going to translate this and to make sure that when that voltage goes from 100 to 230, it's going to smoothly increase airflow from 368 to 5798 CFM. So this shows the RPM versus flow versus voltage. And so you can see as voltage increases that the flow is somewhat nonlinear. It kind of goes up quickly at first and then goes slowly at the higher voltage, and RPM is a little bit more in a line. And again, motor curve is going to take that number on the controller and turn it into a nice straight line for that CFM to make sure it makes sense when we program it. So here for AP as an example are the different motor curves, and when you punch that number into the controller, it shows you what voltage output comes from the controller. So it's pretty interesting if you look at motor curve number 4 and number 8, which are two pretty widely used ones. When a 90 is put into the controller, on motor curve 4, that's going to be 186 volts versus on motor curve 8, that's 128 volts. So depending on what kind of motor's on there, if it was meant for motor curve number 4 and you accidentally put in motor curve number 8, that fan's going to be spinning a lot less than what it would be because it's now receiving 128 volts compared to 186 volts, which is going to probably correspond to the airflow that you were hoping to desire. So each of these motor curves are quite different. Some are a little bit similar to each other, but for the most part, they're really different. And so when these are wrong, it can really result in drastic changes in the environment and generally leads to undesirable effects. So this is a busy graph that shows what this looks like for all 10 motor curves on a controller. So again, this line just kind of again shows that when you punch in a 40 on the controller or a 50 to hit that minimum speed, it's going to correspond to a lot of different voltages. But also notice on this, based on all these different lines, is as that temperature in the room warms up and we have our 2-degree bandwidth where we're going from say 50% to 100%, some of these fans are going to increase really quickly. Some might not respond at all to that change. And so that's where we're going to lose the ability to have a nice smooth transition and reduce issues with causing that room to get maybe too hot or cool too fast, and which could lead to higher energy usage. So it's important to get these motor curves correct. All right, a little bit on current soffits and sensors as I kind of get into the home stretch here. Current leakage can be a big problem because we need them to seal up tight for controlling the static pressure in the barn in winter, and that small cracks are basically unplanned, uncontrolled inlets, which are then going to create drafts for the pigs, which then also could lead, just by making the room ununiform or cooling it down too fast, say if you got a lot of wind, lead to higher energy costs. And so we want to be able to patch these holes up. So for example, to show the impact of a hole or holes, if we have a 1200 head room that's at 6,000 CFM, 2 24-inch fans at 50% would provide that. So if we're trying to hit 800 feet per minute at our inlet, that means we need the combined total opening of all our inlets would be 7.5 square feet, which is probably about a ½ inch or a little less, 3/8 inch opening on all of our doors. A 6x6 hole is 1/4 of a square foot, which is already 3% of our total opening that we need. So if you have 5 holes in your curtain that are each 6x6, that becomes 17% of the total inlet requirement. So essentially 5 holes is equal to 11 inlets open at 1/3 of an inch. And so that's the impact of these holes. And so, robbing 20% of the air we need to go through our inlets to get a good air jet distribution is going to cause problems. It's going to cause the air going through the inlets, the airspeed at the inlet to be lower, which is going to cause it to come out slower. And then it's going to drop on the pigs and create problems in a poorly mixed environment. So the key is repair and patch holes. There's some different materials out there. I know curtains aren't always the easiest thing to repair and have it last, but these holes can be very problematic. And again, sagging is another issue. We want to make sure that we get a 3 to 4 inch overlap on the curtains. Holes patched, end pockets covered. We don't want wind whipping around there, but it's all different ways to do it, but it's important to get it done before it becomes too miserable outside to do it. Sometimes people ask about putting bubble wrap up. This is just kind of a thermal image showing the difference in temperatures. And so the image on the left is bubble wrap. And so oftentimes when it's installed, we need to leave a foot or two at the top, just in case for emergencies. If we lose power or ventilation fails, we need to still be able to have that curtain drop and allow air to get inside the barn. And so that bubble wrap is going to kind of do two things. It might not provide a lot of insulation or R value to the composite wall, but what it really does is it helps seal, and it's going to block any drafts, and it provides an air gap between the curtain and the inside of the barn, which those pigs aren't going to have that radiative heat transfer between that cold curtain that on this day was, they're going to exchange heat with a 54-degree wall, i.e. curtain, versus if they have one barrier such as bubble wrap, the inside there is going to be about 77 degrees. So it's a much warmer surface that the pigs are going to lose less heat to. Again, we want to always make sure our soffits are clean. Even bird netting, even though it seems very open and easy for air to get through, it can collect dust, corn vines, etc. And it's going to have to be sometimes cleaned, brushed off, hit with a leaf blower, especially during this time of year as things get pretty dry and a lot of dust is moving around due to harvest. We just want to routinely inspect them and just, again, make sure that they stay clean, because in wintertime, we're going to be using these soffits for the primary port of entry for air into the attic. And so if this gets clogged, it's going to cause issues down the system. So if our soffit becomes restricted, it's going to increase the resistance on the fan. The fan's going to use more energy and it's going to perform worse. It's going to have a lower airflow rate, which is not going to exchange the air the way we were hoping for inside the barn, which leads to a more humid and poorer environment. So keep the soffits open and clean. Oftentimes barns run east-west, and so if the soffit's on the north side of the barn, a lot of people have closable snow doors that they can close up that to prevent blowing snow and having over-pressurization from that northwest wind. We typically like to leave one or at least about a third of those open, just again to allow that attic to equalize its pressure, and so it doesn't build up on one side and create other problems. But again, we want to prevent over-pressurization and snow from entering the attic. Sensors. Again, we always want to make sure we have multiple probes in the barn because we want an average of that, and we also want to make sure if one goes bad that we have something that there's additional probes to look at. They need to be cleaned. Dust can have an impact. That image shows the change in temperature after the dust was wiped off of them, and so it can have an impact. So we need to make sure those are clean and orientated correctly. We want them close to the pigs, but not at the pigs. We don't want the pigs to chew on them. We also don't want them in front of inlets or heaters. So they kind of need to be at a spot where it kind of reflects the pig area, but is not being hit by cold air or by heat. And then it's in an area that's well mixed. Also don't want them too close to the ceiling or too close to the floor. Lastly, just a few other things to keep in mind if you haven't already done it. We want to make sure that if our mister lines, that we have our water line turned off. Any inline water filters get clean. We power off any of our solenoids. We don't want these things accidentally to come on and getting the pigs wet in the middle of winter. If we have evaporative cooling pads, say on a sow farm, again, water line turned off, pumping system flush, cleaned, winterized, removed. Add any insulation along the inside of the cool cell or curtain to reduce any drafts coming in. Kind of depends on where it's located. And we also, again, take a second to check those backup thermostat settings because we might have been in, summer mode where we might have turned up the heat or the cool one up a little bit just because we had some pretty hot days recently. So we want to probably get that turned back down. And things to think about as we set those settings is, how long can it take somebody to get there? Because that might affect where you set that, because if somebody's quite a ways away, you might need to know a little bit sooner that there's an issue if they can't get there in time to get things situated. So with that, I'd run in, again, the QR code to access that checklist. Hope you all learned something new and enjoyed the presentation. And with that, I will take any questions.
Thanks, Brett. At this point, I am not seeing questions in the chat. So again, if you have questions, please speak up or drop your question in the chat. Brett, you've stepped through a lot of things. In a sense, what would say your top 2 or 3 things that really can make a difference on energy efficiency in these barns?
I'd say the top 2 is going to be reducing infiltration. So just making sure the barn's tight, there's some infiltration that's just almost impossible to fix. But it's all the easy stuff of just keeping the barn tight, sealing unused fans, patching holes, making sure doors are sealed correctly, inlets are installed correctly. Would be mine. And then the other one, again, is controller settings, because if that heater offsets too close and we're overrunning the set point, it's just a really big waste of energy, because we're just exhausting that heat right out. And that's probably one of the simplest ones, just to make sure that fan's not ramping up right after the heater turns off.
I like to call that the roller coaster. And so you got walk in a room, listen for when the heater shuts off, and make sure there isn't a fan that's starting to ramp up. It's pretty easy to monitor that.